Hey nerds, we're doing a bit of science news this week, and it's actually really exciting for me because I got to be involved in this. So, modern lasers are unbelievably intense. Now, maybe not Death Star intense, sure, but we can ionize matter instantly. We can accelerate particles. We can force atoms to fuse. We can create temperatures hotter than the core of a star. But even with all of that, there is another level entirely that physicists have wanted to reach for decades. This is where field strengths are so intense that the vacuum itself becomes unstable. Now, in quantum field theory, the vacuum is not truly empty. It's full of fluctuating quantum fields. A specific type of quantum field theory called quantum electrodynamics, or like QED, this predicts that virtual particle antiparticle pairs appear and disappear constantly without becoming real particles. But if the electric field becomes strong enough, it could supply enough energy over a very small distance to literally pull those pairs apart before they annihilate each other. Now, at that point, the vacuum breaks down and starts spontaneously producing real electron positron pairs. The critical field strength for this to happen is something that's called the Schwinger limit. It's named after Julian Schwinger, who won a Nobel Prize in physics in 1965 for his work in quantum electrodynamics. So the Schwinger limit is essentially the threshold where electromagnetic fields become so strong that they can create matter directly from the quantum vacuum. Now, the value for this to happen is insanely large. Like, it would need a laser with an intensity of about 10 to the 29 watts per centimeter squared. Now, the most powerful lasers in the world today can reach like 10 to the 23, maybe 10 to the 24. And at some point, I will cover this in a separate video, but building these lasers is incredibly difficult. Like, it can take decades to achieve, and it requires whole entire buildings to install and maintain them. And most of the time, that's to achieve just like a tiny fraction of an increase, maybe up to like a factor of 10 if you're really lucky. Jumping from 10 to the 24 to 10 to the 29, that is just not feasible with our current laser technology. But there could be another way. So, a paper was recently published in Nature called Efficiency Optimized Relativistic Plasma Harmonics for Extreme Fields. And it's getting people excited. Now, I was very lucky to get to spend some time working on this experiment and to be included in the author list of this work. But the actual leaders of the project were Dr. Robin Timmis, who's in the same research group as me at Oxford and has proofread this video to make sure that I do not mess it up, along with Colm Fitzpatrick, Jonathan Kennedy, and Holly Huddleston from Queen's University in Belfast. Now, this paper is not about building a bigger laser. It is about compressing light more efficiently. So, laser intensity depends on three main things: how much energy you have, how short the pulse is, and how tightly you can focus it. One of the major breakthroughs that made ultra intense laser physics possible is something called chirped pulse amplification, or CPA. This won like the Nobel Prize in 2018 for Gerard Moreau and Donna Strickland. You see, the problem with trying to make extremely powerful laser pulses is that if you amplify a very short pulse directly, the intensity becomes so high that it destroys the laser material itself. CPA solves this in a really clever way. So, first, the pulse is chirped, meaning it is stretched out in time. So, different frequencies are separated slightly, turning an ultra short pulse into a much longer, lower intensity one. Now, I actually did this in my own PhD experiment last year, but for a very different reason that I will talk about another time. But that stretched pulse can then be safely amplified without damaging the optics. And after the amplification, the pulse is then recompressed back down to an incredibly short duration, restoring like this enormous amount of power into a teeny tiny slice of time. And because power is energy divided by time, squeezing like even moderate energies down into femtoseconds can produce really high peak powers, reaching like terawatts or even petawatts. So CPA is the reason that modern lasers can generate electric fields strong enough to study relativistic plasma physics and laser wake field acceleration. That's me. So, what about getting to a higher regime, though? Well, this paper argues that coherent harmonic focusing might be the next major leap. So, the central physics here is about laser plasma interactions. When an ultra intense laser hits a solid target, the surface ionizes instantly and it becomes an overdense plasma. Now, at these intensities, the plasma can behave like a relativistic mirror. We'll come back to that in a minute. The electrons at the surface oscillate violently under the laser field, and the reflected light becomes highly non-linear, leading to what's called high harmonic generation. So, for that reason, high harmonic generation is what's called a non-linear optical process. And this is where extremely intense lasers interact with the material and then generate light at new frequencies that are multiples of the original laser frequency. So, think about it this way. Under normal conditions, if you shine a light through a material, the response is what we would say to be linear. So if you double the intensity of the light that you send in, it will double the intensity of the light that you get out. But at very high laser intensities, the electric field becomes strong enough to distort the behavior of the electrons inside the atoms of the material that the light is traveling through. So, this high harmonic generation was first developed in gases, and this is where an intense laser field can rip an electron away from an atom, accelerate it, and then drive it back into the parent ion. When the electron recombines, it releases its excess energy as a burst of high frequency light. Now, because this happens repeatedly every laser cycle, the interaction generates harmonics of the original laser frequency. Now, gas-based high harmonic generation is what originally enabled attosecond pulse science, but this is fundamentally limited in the energy and the intensity of the pulses that it can produce. But this new paper is using a completely different mechanism: relativistic harmonic generation from an overdense plasma surface. So instead of electrons recombining with atoms, the plasma surface itself oscillates relativistically under the laser field and then imprints harmonics onto the reflected light. Now, because solid density plasmas can survive much more intense laser fields than gases, this approach has the potential to generate much more energetic attosecond pulses. So the actual paper reported on the measurements found between roughly the 12th and the 47th harmonic, but on the experiment, it was likely that we observed harmonics beyond the 100th order, possibly even up to the 200th order. Now, high harmonic generation is incredibly important because it allows us to generate ultra short attosecond pulses, these flashes of light short enough to probe the electron motion inside atoms in real time. It's one of the key techniques behind attosecond physics and modern ultrafast spectroscopy. This is because shorter wavelengths of light can be focused into smaller spots. But instead of trying to massively increase the laser energy itself, you can potentially increase intensity by generating very high harmonics and then focusing those coherently into an extremely tiny region. That's what's called coherent harmonic focusing. To do this, you need to use a plasma mirror. So, like I said earlier, in ultra intense laser physics, if you hit a solid surface with a sufficiently powerful laser pulse, the outer layer of the material is instantly ionized into a plasma. Now, at lower densities, plasma will appear to the laser to be transparent, or it might absorb some of the energy. But once the electron density of the plasma is high enough, it can behave like a conducting surface that can reflect electromagnetic waves. It loses its transparency, basically. Now, right at the moment of peak intensity, the plasma forms and then acts like an ultra fast mirror for the main laser pulse. And what's important here is that light carries momentum. So at extreme intensities, the laser actually dents the plasma mirror inwards. So the plasma effectively becomes a self-shaped focusing optic. The laser creates the plasma mirror, then reshapes the mirror through radiation pressure, and then the harmonics get focused by the curved plasma surface itself. To be clear here, physicists already knew relativistic plasma harmonics existed. Like, that's not the breakthrough that we're talking about, but the problem was efficiency. Theory predicted that you could get extremely strong harmonic generation under the right plasma conditions, but experiments consistently underperformed. What this work today demonstrated was a major technical milestone that may make those future experiments a lot more realistic. So, the achievement is that the plasma harmonic generation finally behaves as efficiently as the theory predicted that it should. We can do it in an experiment. So, why am I telling you about this? Like, why should you care? Well, this opens a potential route towards studying genuinely extreme field quantum electrodynamics in the lab. So, things like vacuum pair production, photon photon scattering, and nonlinear quantum effects, ultra intense attosecond physics. Another paper from our group from a few years ago that was led by Zixin Zhang used large scale simulations to model how ultra intense laser fields could produce things like vacuum birefringence and even photon photon scattering, where light effectively interacts with light through the vacuum. The key idea in both papers here is that once electromagnetic fields become extreme enough, the vacuum stops behaving like empty space and it starts behaving more like a non-linear optical medium. So, in ordinary optics, nonlinear materials can generate harmonics and mixed frequencies together. And the fascinating thing is that quantum electrodynamics predicts that the vacuum itself should eventually do the same thing. So while this harmonic generation experiment is still nowhere near breaking the vacuum, it's part of this much bigger picture, this much bigger direction in laser physics, using plasma interactions and extreme field compression to push light into regimes where the structure of empty space itself can be explored experimentally. Now, I am super honored to have been a part of this work, and I am so excited for the team and what's to come. And you should definitely be keeping an eye on high harmonic generation. Anyway, back to Wakefields for me. Stay nerdy.